All right, good morning, everyone. Sorry about the little bit of delay. There was a couple of people that had some difficulty getting in that I had to kind of help out. But just to introduce myself real quick, my name is Chris Glover, and I support the aftermarket sales here at Airxchange. And for about the next half hour, I'm going to be discussing some frost control strategies. Okay, so we had a pretty diverse group of people who signed up for this presentation. So what I tried to do is create a presentation that could appeal to a wide audience. Some of this may be completely new to you, and some of this may be a refresher. But regardless of your background, I'm hoping to touch upon multiple areas of interest. Okay, so during my time here at Airxchange, one of the frequently asked topics is for me to discuss frost control. And with everyone talking recently about the polar vortex, I thought what better time than now to discuss it and in a more general context. So on the agenda today, we will look at the typical winter operating process, the psychometric process, and the theory behind when frost forms, and to end with the most common strategies for controlling frost. After which I'll open up the mics so that everyone can have an opportunity to ask any questions that you may have. So just as a refresher, energy recovery is used in the wintertime to recycle the heat and humidity contained in the exhaust air and use it to heat and humidify the incoming ventilation air. Fairly simple process. Looking at a typical system, the outside air comes into the unit and is heated by the primary heating and cooling element to a temperature that is suitable to be delivered into the space. And that heated air dilutes the space air with fresh air, and the stale air is then exhausted back through the unit. Now, at this point in the process, the air is typically warm and has picked up a bit of humidity, and you can use that to perform work on the incoming ventilation air. Now, let's look at that same process, but adding an energy recovery wheel to that system. So instead of the primary heating element having to treat the entire ventilation load, the energy in the exhausted air performs a large portion of the work, which reduces the capacity required by the primary heating element to do the same amount of work. I often refer to this as this process as a load shift, where you're shifting the heating load over to the wheel and still accomplishing the proper ventilation to the space. Now, pulling that wheel out of the system, let's take a closer look. Here you have outside air coming in at 20 degrees, and you have the exhaust air leaving the building at 75 degrees. A percentage of that heat is going to be used to warm the incoming air to 63 degrees. And since that heat was used up in exchanging it to the ventilation airstream, it means that the leaving exhaust air is going to be a lot cooler. So what does it take to generate frost on an energy recovery wheel? Well, you really need two things. You need the temperature to be at or below freezing. And if you look at these temperatures to the left over here, I'm going to highlight them. You can see that they are definitely at or below freezing. And secondly, you need a source of liquid water. Now, one of these items really isn't available during most normal winter operating conditions, and that's liquid water. And that's due, in fact, because the energy recovery process, or the humidity transfer process, is transferred through the method of adsorption. Adsorption and conversely desorption is the transfer of water in the vapor phase. So now we're going to take a quick look and discuss a bit of theory regarding the frosting process. The next couple of slides are going to use a psychrometric chart to kind of visually demonstrate what's happening in the ERV winter operation. I'm by no means expecting everyone here to be an expert on psychrometrics. If you haven't seen one of these in a while or never seen one of these, don't worry, I'm going to explain a few key items, but I use this as a visual tool because I think it does a good job of explaining what is actually happening in the system. So first, the horizontal axis at the bottom represents temperature. The very cold temperature is on the left-hand side of the chart, and as the air gets warmer, it moves to the right-hand side. The vertical axis represents humidity, starting with low absolute humidity on the bottom, and as the condition gets more humid, it moves to the top. The curved lines in the middle represent relative humidity. Relative humidity is a measurement of how much humidity is actually in the air as compared to how much there could be, starting at 0%, which is completely dry, to 100%, which is completely saturated. The top curved line represents when the air is completely saturated. This means that the air can't hold any more water. I'm going to refer to this as the saturation line or the saturation curve. Remember that when air has reached this point of the process, the air has reached 100% relative humidity. That means it simply cannot hold any more water vapor. And what typically happens when air reaches 100% relative humidity? Well, if you're outdoors, it could start to rain. It's when the vapor in the air could potentially condense and form liquid water. And I'd like you to keep that in mind as we go over the next couple of slides. Okay, so borrowing from our previous slide, let's plot that process on the psychrometric chart. Our outside air is 20 degrees. You can see it on the chart right over here. And our exhaust air is going to be 75 degrees. Now let's draw a line between these 2 points. This line represents the energy recovery process line. At any given point in determining how effective the wheel is, the leaving supply and exhaust is going to end up somewhere on this line. I'd also like to let you take note of the different state points, and in this particular case, which airstream holds the most amount of humidity. Well, if you remember from a couple of previous slides, I said it starts where very dry air moves up to more humid air. You can see that this point, which is your exhaust point, has the most amount of humidity, and it's good to keep that in mind as we discuss the frosting process. Now, this particular process, as you see up here, has resulted in 2 leaving conditions. The supply air is at 63 degrees, and the leaving exhaust air is 32 degrees. If you remember when I said that you needed liquid water to form frost, in order to condense water on the heat exchanger, these points have to become saturated. All the moisture exchange for this process so far has been done in the vapor phase. Neither airstream has approached the saturation curve. Energy recovery is fairly unique in this regard because as the exhaust air gets cooled, it's also dried, which means the leaving air naturally wants to move away from the saturation curve. It's because of this unique process which really minimizes the risk for frost. So keep that in mind. The thing to take away from the slide is that in order for water vapor to condense, this process line has to come in contact or close to contact with that saturation curve. Now let's take that same example and lower the outside air temperature. Let's go to 0 degrees. And let's plot that same point. Plot the supply leaving air, representing that red dot, and now the exhaust air. You can see that the process line comes closer to the saturation curve, but still hasn't intersected it. So theoretically, this process shouldn't form frost in this operation. And this is even with temperatures that are significantly below freezing. And the reason I'm showing you these conditions is because I want to demonstrate that the outside air temperature usually isn't the biggest determining factor from when frost forms. Let's take a look at one more condition. Let's keep the outside air at the same point and raise the humidity of the exhaust air. Now let's plot the supply air condition once again and the exhaust air condition. Now, what's different about this process versus the previous ones that we looked at? Well, in this particular case, the process line has come in contact with the saturation line. You can see it's come in contact right here. So what did it really take to accomplish that? Well, we had to raise the indoor humidity, right? Remember a few slides ago when I pointed out the humidity levels? It's because I wanted to demonstrate the impact that indoor humidity makes when determining whether there is a frosting condition. So in order to generate frost in this particular system, we had to raise the indoor relative humidity pretty significantly. Another thing that I like to point out that I've accumulated over my years here at Airxchange is, as a rule of thumb, most commercial spaces have a tendency to dry out during the winter months. So in a practical sense, while the design may have started with a high relative humidity, the actual operating condition might be quite lower than that. So now that we've generated a process that could result in frost, what are the popular methods to allow a wheel to work in these conditions? The four most common strategies in the market are preheat, and I should mention that preheat is the only method that I'm going to discuss today that allows the wheel to operate at its full potential in these conditions. The second method is wheel speed control. The third is airflow bypass, and the fourth is stop jog. And I'm going to go briefly over each of these type of schemes. So regardless of how you're going to control frost, first you need to determine whether there is a frosting condition. The easiest way to accomplish this, I would suggest using the Airxchange web-based selection software, Airxweb. So you would go to www.airxweb.com. Once you open up the software, you're prompted to create a new project. As part of that process, you're going to enter into the software your location and operating conditions. You would then add a wheel to the project, and if these conditions result in frost, the program is going to alert you to that and provide the frost threshold control point. And if you're using preheat, it would also provide the requisite heater size as well. So starting with our frosting process, let's take a closer look at the preheat option. Keep in mind that the preheat is the only method that I'm going to discuss that allows the user to get the full potential performance from the wheel during a frosting condition. The preheat method is when you add a heater to the system to slightly preheat the incoming air that's going into the wheel. And while yes, the purpose of the heater is to warm the air, but the true benefit of adding a preheater is to lower the incoming relative humidity of that air prior to it entering the energy recovery wheel. It's because of this that you really don't have to heat the incoming air to 32 degrees. In this case, in order to stop the frost from forming, we're only heating the air to 10 degrees. So let's take a moment and plot that process on the site chart to see what's exactly happening in the system. So starting with 10 degrees, the air goes through the heater and is warmed up slightly to 10 degrees. This is going to warm the air and lower the relative humidity, which changes the slope of the process line. And it changes it enough so that all the operating points are no longer in contact with the saturation curve. So theoretically, all it needed was a small amount of heat in order to take this tangent off the saturation curve. So all your operating points no longer become saturated. And as you can see, it only takes small amounts of temperature, and you can have which could have a substantial impact on the slope of that process line. Here you can see what happens to your discharge temperatures. So adding 10 degrees doesn't really have a tremendous impact on your discharge temperature and your exhaust air temperature. Another thing I like to mention is that a lot of people only consider preheat on the outdoor air side, but you can preheat air on the exhaust air side as well. You may notice that the heater, or the amount of heat required, is more. In this particular case, a 25-degree rise versus a 10-degree rise on the outdoor air side. But in this configuration, the energy recovery from the heater is recoverable. So if any process results in moving the two operating points away from each other, that results in a recoverable process. That means that the heat that's added to the system when you put the heater on the exhaust side can be added it gets added to the discharge condition or the leaving air condition. So now we're coming off the wheel at 75 degrees versus, I believe it was 58 in the previous slide. So now that we kind of discussed the theory behind preheat, let's talk about the practical application and integrate that into a control scheme. First, you have to determine if your system is subject to frosting. And if it is, what is the frost threshold point and what size should your heater be? Once again, the easiest way to calculate that is to use the Airxchange design software, AirXWeb. After entering the design conditions in the software, it'll tell you what the control point is and the size of the heater required to maintain that inlet temperature. You would then use a dry bulb sensor to monitor the outside air temperature entering the wheel. And if that temperature drops below the frost threshold control point, you would turn the heater on and modulate to maintain that predetermined inlet temperature. Pretty simple system. As a rule of thumb, preheat frost control works best for applications that have a moderate to high indoor humidity or extremely low outdoor air temperatures. Some examples of these kinds of spaces would be buildings that have mechanical humidification, pools, spas, yoga studios, gymnasiums, athletic facilities, and so forth. Okay, the next method that we're going to talk about briefly is wheel speed control. Wheel speed control is another very popular method to mitigate frost. With wheel speed control, the premise is to slow the wheel down to warm the core temperature. By slowing the wheel down, you're also minimizing the wheel's ability to transfer heat and humidity. Plot this on the chart. So as the wheel starts to slow down, the leaving conditions gradually get closer to the entering conditions. The exhaust air is going to get a bit warmer, and the supply air is going to get a bit cooler. So slowing the wheel down has moved these two state points away from the saturation curve. One of the things that you may have noticed during that animation is that the points don't move up and down the standard process line. And that's because as the wheel starts to slow down, it becomes more sensible in nature. So looking at the resulting process, you can see that you're not getting as much work out of the wheel given these conditions. So you're going to have to take that into consideration when designing your system. So integrating wheel speed control into a system, once again, use the Airxchange software to determine if you have a frosting condition based on the operating conditions. If you do, there are two common ways to set up the system for wheel speed control. The first is a series of dry bulb sensors, one located in the incoming outside air to monitor whether the temperature is below the frosting threshold, and the other would be located in the leaving exhaust air to modulate the wheel speed to achieve a desired leaving air temperature. Now you may be asking yourself, what temperature would that be? How do I determine that temperature? Well, oftentimes you would refer to a manufacturer provided chart like the one on the left. Here you can see here, based upon temperature and humidity, it's going to give you a design temperature and give you the proper exhaust air temperature that you have to modulate the speed to achieve. So you have to be at or above that exhaust air temperature. The second way to accomplish control would be to use a dry bulb sensor on the outside air and a relative humidity sensor, once again, in the exhaust air stream. But instead of modulating the wheel speed to achieve a certain temperature here, you're modulating the wheel speed to achieve a desired relative humidity. In most cases, you want to keep the leaving relative humidity below 90%. Because of the unique nature of the more sensible process that wheel speed has a tendency to operate at, as a rule of thumb, wheel speed control is best suited to low humidity spaces and moderately cold environments. So typical spaces that I see this being used is K through 12 classrooms, office space, retail, and so forth. Okay, the third method that we're going to discuss is airflow bypass. Airflow bypass works on a similar principle as wheel speed control, where you're trying to minimize the wheel's ability to transfer heat and humidity. By bypassing a portion of air around the wheel, you're essentially minimizing the pool of energy that you can use to treat the air. However, unlike wheel speed control, which follows that odd performance path, when using bypass dampers, the operating points are going to follow the typical process line. So as you start to bypass air around the wheel, the leaving exhaust air is going to start to warm. And conversely, so does the leaving supply air. Now, if you look at the state points, this may appear to be a win-win situation where you both stop frost from forming as well as achieve the higher leaving air temperature. But the thing to keep in mind with air bypass is that you've also bypassed a portion of air at essentially 0 degrees in this case that is now mixing with the discharge temperature leaving the wheel, which actually is going to result in an overall lower entering air temperature to the primary heater. So once again, you would have to take that into consideration when designing the system. So integrating, that should say airflow bypass, I apologize. So once again, integrating airflow bypass into a system, you'd use the Airxchange software to determine a frost threshold. Anyone noticing a trend with that first bullet? So since this process is so similar to wheel speed control, you're going to use the same methods. So you would either use a set of dry bulb sensors or a dry bulb and a relative humidity sensor. And you'd also follow the same steps. So in both systems, you'd use the dry bulb sensor to monitor whether the outside air temperature is below the frosting threshold. And you would use the subsequent sensor on the exhaust air side to modulate the damper to achieve a desired either leaving air temperature or relative humidity. Now, because bypassing air follows a more traditional performance path, it's a little bit easier to use in more applications. So it can often be used more reliably than wheel speed control in applications where relative humidities will be higher or start to rise. Therefore, kind of as a rule of thumb, bypass I see used a lot in moderate to low humidity spaces and moderate to colder environments. Typical building spaces that I see it being used would be universities, schools, research buildings, and gymnasiums. Okay, the last method that I'm going to talk about is stop jog control. The stop jog method typically uses a single dry bulb sensor on the outside air temperature. Once again, that outside air temperature is going to measure whether the temperature is below the frost threshold. And if it is, it's going to tell the system to stop and start the wheel intermittently to keep frost from forming. It keeps performing this process until the outside air temperature is above the frost threshold. This method gets you what I call slugs of performance. So when the wheels, you're going to get performance from when the wheel's spinning, but zero performance when the wheel's sitting idle. Because of the unique operational nature of this method, I usually suggest not necessarily used in a specific humidity environment, but more where there's only a handful of hours that you could find that are below the frosting threshold, which actually can be quite a few areas of the country when you really dig into the actual operating conditions. So as a rule of thumb, I would say stop jog is best suited for not necessarily humidity range, but in climates where the operating hours below the frosting threshold are going to be minimal. Okay, so I went through quite a bit of information there, touched on a lot of different subjects or a lot of different systems. I'm not expecting everyone to remember everything, so I'll tell you where to go to find out more. First, I would start off at our website, www.airxchange.com. Here you'll find access to all our technical materials. So the topics that I was talking about today are actually in a technical note. It's the tech frosting that's on the website. Feel free to download it. It goes into a little bit more technical definitions or detail of what we spoke about. We also have access to case studies, relevant industry information, our contact information, and links to the software that we discussed during the presentation. Also on the website, and this is kind of a personal plug, you'll find access to our aftermarket section, which features an online parts lookup and a selection tool that helps essentially those who are in charge of servicing and maintaining wheels. You'll also find access to our replacement wheel products. Our replacement wheels are designed to assist those who are in need of replacing an older inoperable wheel, and that's any manufacturer's wheel. We've also just recently launched our new web-based software. I'm very excited about that. So if you go to www.airxweb.com, this new software keeps all of our configurations updated in real time. It also saves your information in the cloud, and it lets you communicate with those who have the tool, inter-office sharing as well as sharing with Airxchange remotely. It's a really neat tool, and I hope you get a chance to check it out. And lastly, if you need to get a hold of me, here's my contact information. Feel free to reach out. I'd love to hear comments on this presentation, whether you found it helpful or not. I'd also like comments on any ideas for future presentations, if there's things that you'd like us to discuss. Or if you just have general questions that you need answered, I'm happy to do that as well. So with that said, I'm going to go and open up the ability to chat here. So if you have a question that you'd like to ask, feel free to type it into the chat box or just mention it over the phone. Okay, everyone should be open now. All right, well, it doesn't look like there's too many questions, but like I said, if you do have questions, feel free to give me a ring or send me an email. I'd be happy to assist. Otherwise, thank you very much for attending and have a great day. Take care, everyone.
Thanks, Chris. Appreciate it.
Thank you.